Hello everyone. What I want to do in this video is talk about little LP, and for P between 1 and infinity, I want to prove that it defines a normed vector space. So what is little LP? And I like little LP because it's probably one of the simplest non-trivial examples that we'll see in this course of a normed vector space. It's a little more exotic than just regular Euclidean space. All right, so really to define this, you can pick anything between 0 and infinity. So this is all sequences. Let's I like to call them Z. It's all sequences Z of complex numbers where this is finite. Okay. This does not make sense for P is infinity, so little L infinity is really just all bounded sequences of complex numbers. And of course, we can quantify that by saying this supremum here is finite. Oops. And this is just the usual absolute value on complex for complex numbers. Okay. Yeah, so the little LP norm for P between 0 and infinity is going to be as follows, and it technically is not a norm, as we'll see in a second. For P between 0 and 1, I'll still call it the LP norm. And the little L infinity norm is exactly just this supremum here. Okay. So yeah, these are the norms, quote unquote norms on little LP. So for any Z in LP, two things are true. So in some sense, it's almost a norm for all P between 0 and infinity. And these are trivial to check. The little LP norm is equal to 0 precisely when we have the 0 sequence. And if alpha is a scalar, a complex scalar, then we can pull that out with an absolute value. So I claim that the triangle inequality fails if P is between 0 and 1. And we don't have to dig terribly deep to see this. How do we see this? So let's say X is 1, 0, 0, etc. And Y is a gazillion similar examples you can cook up. So X is all zeros except one in the first spot. Y is all zeros except one in the second spot. Okay, so this is just 1, 1, 0, 0, all zeros here, little LP. And this is pretty trivially 2 to the 1 over P, whereas these two, both 1, so this is 2, okay? All right, so what do we have? This is a P, sorry about that. So when I write this is the statement. It could be true, it could be false. We're going to figure out when this is true and when this is false. In this example here, this is true if and only if 2 to the 1 over P is less than or equal to 2. This is less than or equal to 1. Well, 2 to the x is increasing, so this has to be, and 2 to the 0 is 1. So this is true if and only if 1 over P minus 1 is less than or equal to 1. And this is true if and only if P is bigger or equal to 1. P is a positive real number, bigger or equal to 1. Okay. So in other words, this is false. So we've carefully proven that this example here is false if P is between less than 1. Okay. All right, so I want to show that the little LP norm does satisfy the triangle inequality when P is between 1 and infinity. And I'll show that we do have a normed vector space when P is between 1 and infinity. So for any x, y, and LP, following is true. So I will focus on P strictly between 1 and infinity because you can check as a very easy exercise that when P equals 1 and P equals infinity, this is clearly true. So yeah, so this is genuinely easy, and dare I say, use the kind of the T word. It really is trivial if P equals 1 or P is infinity. All right, so without further ado, let's get to this goal. So it's not the quickest proof. The same proof basically tells you that big LP is a normed vector space for P between 1 and infinity, including P is 1 and P is infinity. And that's basically, you can think of it as an exercise once we finish this for big LP. And you can cook up an example kind of like this where probably a good exercise. Big LP does not satisfy the triangle inequality when P is between 0 and 1. Okay. All right, so I need first a lemma called Young's inequality. if you do PDE research, partial differential equations research, this pops up all the time in partial differential equations. So what this is saying is, if I have two non-negative numbers, and I have the conjugate exponents to P being Q, remember, P is strictly between 1 and infinity, so Q is actually just, you can solve for it, it's just P over P minus 1. So this is going to be A to the P over P plus B to the Q over Q. And it's an easy consequence of convexity. Let's say f of x is e to the x. So this, of course, is e to the x. It is bigger than 0 for all real numbers. And so that means this is convex on R. So what does that mean? If I have, I'll draw a picture to explain this if you haven't seen convexity before. So strictly speaking, convexity is the following. Yeah, and I'll just draw the picture before I even explain what this means. Okay, so I'll go back to what this means in a second. So the picture is as follows. We draw e to the x, something like that. All right, so for graphical purposes, I'll pick, let's say, a U here and a V here. Okay, so I have my points roughly here. Okay, so I have f of my 2 points here. Okay, so this here represents something in the line segment between U and V. And as lambda varies between 0 and 1, we have everything in the line segment between U and V. So let's say this is, say, right here, lambda U plus 1 minus lambda V. Okay. Okay, so this point here, you can check. Well, this is the x value, of course. Yeah, this is going to be a little hard to fit. So here's what I'll do. The x value here is this right here. And you can check that the y value of this point here is just simply lambda f of u plus 1 minus lambda f of v. Okay. basically going back to Calc 3, this is the point on the line segment containing these 2 points in the xy plane, corresponding to this x value. Yeah, this red line here is the line segment containing these 2 points. On the other hand, let's do a different color. This point here, same x value, but the y value, to put it here, is, well, f of this x value. Okay, so basically this is saying line set, so this is literally saying convexity, that the line segment containing these 2 points here sits above the actual graph. That's exactly what convexity says. It's this line segment here sits above this graph here. Okay? And the y value for this blue point is exactly this here. So, okay, maybe let me do this. So this is blue, so maybe I should use blue for this one. Good. Second. So I just circled is a y value for this point. And the definition says this is bigger or equal to the green y value, which is right here. Okay. This right here is this y value. This right here has y value, this one here. Okay. So yeah, that's what convexity says. All right, so yeah, so let's use convexity in a useful way. This is trivially e to the ln of a plus ln of b. This is equal to e to the 1 over p ln of a. And we have to multiply and divide by p and q so that I'll do purple. I get, if this is lambda, then this is going to be 1 minus lambda. So this is lambda u, if I set this to be u, plus 1 minus lambda v. Okay. So convexity says this is less than or equal to lambda f of u plus 1 minus lambda. Just going back to here, 1 minus lambda f of v. F of v is e to q b. So that's equal to 1 over p, a to the p, plus 1 over q, b to the q. And I should say that's a pretty good Taylor series exercise to show that if the second derivative is positive, bigger or equal to 0 even on an interval, then f is convex on that interval in this sense. Just Taylor's theorem. Okay. All right, so now we can get to Holder's inequality, discrete Holder's inequality. really Hölder's inequality. That's how you pronounce it in German. I always feel like it sounds so weird saying Hölder's inequality, but anyway. All right, so this says if WZ is in, sorry, W is in LP, Z is in LQ, then if we have the usual dot product, I'll explain what that is in a second if you've not seen the dot product. That's bounded by the LP norm of W and the LQ norm of Z. And we'll show that this sum here, the dot product, is actually absolutely convergent. So in particular, this is a complex number, or maybe it makes more sense to do it like this. And these double dots, remember, means defined is, well, whatever. So it's a definition. So W dot Z is defined by this sum here. So this is not an inner product. We're not taking complex conjugates here. Okay, and the proof is actually pretty straightforward. Using Young's inequality. So I'm going to prove that this quantity here this is going to be less than or equal to 1. If this is true, I can just multiply by the norm of W times the norm of Z. So in particular, if this is true, and this is trivially, I can smash in absolute values. Then this is going to be P. Okay. So this is what we need to do. Okay, so I'm going to bring the W inside the W norm of W norm of Z inside the sum. And again, it's perhaps not justified that I'm saying it's a norm because I still have to prove that it's a norm. If I do that, yeah, so I really want to look at this, and I'm doing this because I want to use Young's inequality. So let's say this is A, this is B. So this is less than or equal to just by Young's inequality, and I'll skip the step of breaking it up into two sums, but yeah, this is just literally from Young's inequality. Clear. And then we have 1 over q, this sum here. Z, and we're basically done, actually. If you think about it. We're almost done. So this is going to be 1 over p times this here. Plus 1 over q. I'm just literally pulling out the 1 over p and the 1 over q, absolutely trivially. And the reason why I'm doing this, it should be apparent. Whoops, sorry. So this is literally, and by definition, I mean literally, this is not even like, there's no computation, it's not even easy, it's literally by definition the LP norm to the P. Raising it to the P gets rid of the whole thing to the 1 over P. And this literally here is, by definition, the LQ norm. See how much battery life I have. Okay, should be no problem. So these two together multiply to be 1. So it's 1 over P. These multiply together to be 1. So it's plus 1 over Q. Well, because they're conjugate exponents, this is equal to 1 as desired. So we have proven star. Okay, so now we can finish up and prove the triangle inequality. Okay. Okay. Right. So it's proof of the triangle inequality for P between 1 and infinity. Okay. So what I want to do is the following. So I said this, and you can remember, you can check it. Solve for Q, you get Q is P over P minus 1. Okay, so let's say let me set Z to be the following sequence. This will just be convenient to look at. Okay. Okay, so remember what we need to prove. We want to look at this here, where we have sequences x and y and little lp. Much easier to look at raising it to the p. Okay. Yeah, so this is going to be, by definition, the following. Okay, and perhaps not super subtly. So I want to use Holder's inequality, and I have to be a little judicious in how I use Holder's inequality. But given that the conjugate exponent is p over p minus 1, maybe it's not so subtle that I want to break this up in the following way, and maybe it'll work. 1 plus p minus 1 as an exponent is equal to p. So, sorry, I got a lot of wires floating around here. Gotta move my foot. There we go. Okay. So actually, my apologies. I don't want to use Holder's inequality just yet. I need to use the triangle inequality first, just a trivial complex number triangle inequality. So I'm going to use that here. So this here is less than or equal to xj plus yj. So I break the sum up. Now this step is definitely a bit maybe subtle to motivate. Like, why would you want to do that? But I guess it's not so bad, because when I use, ultimately I want this to be less than or equal to the LP norm of x plus the LP norm of y whole thing to the p, and maybe this will work in doing that, because when I do Holder's inequality, I will get something involving the LP norm of x and the LP norm of y, plus some other stuff. And hopefully the other stuff is not bad. And in this case, it really isn't. So I'm going to use Holder's inequality twice. One here. So I do Holder's inequality for this sum here. Remember, this is z here. So this is going to be less than or equal to the norm of x, LP norm, and then the LQ norm of z. Same thing here. Use Holder's inequality here. It's the LP norm for y, LQ norm for z. And really, I'm using basically this one here, after, where I'm multiplying by norm of w, norm of z. So I'm using kind of the smashed in absolute value form of Holder's inequality. Or if you just want to think these are your two sequences, instead of x, it's, the sequence is absolute value of the xj's and absolute value of the yj's instead of y. But basically use Holder's inequality here. All right, so this is going to be equal to the following. Yeah, this is kind of what we want. We are missing missing a raise to the p here, but maybe that's okay. And we have to do something about this here. So let's take a look at what this is. And we'll see that basically finishes the proof. I'm glad it does finish the proof because my battery is running out. Yeah, so this is equal to, so remember this is Z is a sequence of these right here. And sorry, that should be a J, not an I. Sorry about that. Take this whole thing to the 1 over Q. Each term is X plus Y absolute value. P minus 1, but remember Q is P over P minus 1. Okay. So this becomes P. Okay. And I'm going to write this in the following way. Put a 1 over P, but I don't have 1 over P, I have 1 over Q. So what I do is I make this a P over Q. So if you multiply these two exponents, it's 1 over Q. And this is just P over P minus 1 times P minus 1 is P. So I'm not doing a whole lot here. So this is the LP norm of X plus Y to the P over Q. So what have we proved? We've proved that the LP norm of X plus Y is less than or equal to the LP norm of X, LP norm of Y, times the LP norm of X plus Y to the Q over P. But remember, what is that? Well, that's P over P minus 1 over P. So that is 1 over P minus 1. One second. So I'm going to divide sorry. So this is a P here. Forgot about that. This is a P here. Yeah. So it's this to the P. I'll put this in blue. This whole thing here is less than or equal to this here. And we computed this to be equal to this. So it's X plus Y LP norm to the Q over P. Okay. So yeah, we divide okay. But you can check that this is simply this is just let's see 1 second. Yeah, this is just simply 1. Sorry. This is, yeah, it's looked a little funny, but that's all right. This is P over Q. And P over Q is going to be P over P minus 1. So that's P minus 1. So this is, so divide, sorry about that. Well, we're done because this is equal to 1. So this is equal to 1. So I'll erase it. Now, there is a subtlety here, and if you think about it, that is, in theory, both sides could be infinity. And then we can't divide by infinity. So this and this, so yeah, this term and this term, they in theory could be both infinity. Well, what you could do is, instead of defining sequences as infinite sums, just start off with finite sums, and then get an upper bound like this for the LP norm of the finite sum truncation of x plus y, and then let that go to infinity. The sum from j equals 1 to k, for example, then let k go to infinity. This we're assuming is finite. This is purple here because x is an LP and y is an LP. So that easy little argument takes care of it. What I said, I think, is a good exercise for you to do what I just said to get rid of that subtlety here. But anyway, yeah, hopefully that was helpful and useful. And next I will prove LP and little LP and big LP is complete. All right, so long, take care. Bye-bye.